Live?
Yeah. Oh, I don't know if it's live, but
Recording live.
yeah, it's recording now.
All right. Okay, so
You ready?
Yeah.
All right.
So today's topic, we're going to be discussing spatial relativity. And spatial relativity, I'm going to turn this on because it's kind of creepy looking at this. Spatial relativity is a concept that I came up with on accident. And it really was more of a creative extension of Einstein's thought experiment, where Einstein said, hey, I wonder what it would be like to travel next to a bolt of light as it's traveling through space, how that, and that led him to discussions of relativity. So behind us, we have an invention that I created in 2016 as an extension of consciousness research that was going on around the globe. And when I came up with it, it is a coherence detector, basically. You can go to our website and check out more information on that. But it has 10 lights on it, which respond to fluctuations in electromagnetic spheres that it's in the presence of. And so when people go into a coherent state, it's measurable, it's viewable, you can see it happening. And I was looking at it, it was like, oh, this kind of looks like a clock. And that got me thinking, well, what is this relationship to time? Because where isn't time? Okay.
Time is everywhere.
Time is everywhere. So you can't really go in. I don't see how you can go into experiments or discussions about the nature of reality without including time, really light. Where isn't light? Light is everywhere. And consciousness. Where isn't consciousness? In order for anything to be perceived, it has to be perceived by something that is consciousness, that is conscious.
Yes, the nature of subjectivity.
Exactly. And without delving into the different variants of consciousness, I looked at this as a type of quantum clock. And I say quantum because the data that it's reading has a quantum noise source, and we can observe the passing of time through it. And I believe that, and part of our research is including to take this concept and actually start measuring time and create a more comprehensive piece of equipment. But I do believe the way it stands now, if a person were to look at the research and understand the laws of general and special relativity, the concept of spatial relativity should make perfect sense. And so basically there's, in this instance, we're talking about two things: how electromagnetic fluctuations in space affect time, and then also how consciousness plays a role in that. So in this model, anybody watching this, we have to have the assumption, because the one assumption that we are definitely working on is that the decades of research at Princeton, I.C.R.E.A.M, and our own research shows that consciousness has an effect on this lighting. So that's a premise we just accept. And if anybody's watching this who doesn't accept that, we have lots of research to show that. Just contact us and we'll have that discussion. So the second part of that is why is time relative around this? If you look at the nature of relativity, special and general relativity, it generally discusses things that are happening in deep space, as light from a distant star passes by a planet with gravitational mass that will cause the light to bend and space to bend with it. So time, what that shows is that time and space are like two sides of the same coin. As space shifts and bends, time does so with it. And then the other part of relativity is the body in motion. You have two stationary objects. One shoots off, moving, time as measured will be slower for the body in motion than the person standing still. So those are very widely accepted truths and accepted. So those are also, we're accepting those as assumptions as to be true. Now,
building off of that framework.
Building off of that framework.
Spatial relativity.
Right. So again, but this is, I think what a lot of scientists may argue with this is because they're going to argue with it no matter what. Right. But this is not something that I came up with by looking at all the laws of special relativity, looking at all the laws of general relativity, and trying to figure out something that fit in between.
Yeah.
That's what most of science is doing right now. Right. I'm sorry, in
for
this
relativity and
issue.
Quantum mechanics
Yes.
too, especially.
Yeah. So
black hole information paradox, stuff like that.
Right. And that have absolutely nothing to do with this process.
This is not a theory of everything, people.
Absolutely not. And it was not intended. This is an actual. So the theories that we're talking about is to describe a physical thing, not abstract, speculative ideas that can never be tested. Everything we're talking about can be tested. I believe so.
Can be tested or has already been tested. Has already been tested. Or is undergoing further testing.
And we've already done the groundwork to substantiate the need to do that further testing.
Yeah.
And we have that right behind us. And so we know that as light is passing past a body in mass, it's going to slightly bend, and that bending time dilates in that. So if we look at just here, there's a light on this can moving towards us. The light doesn't pass through us necessarily, but it does bend around us.
Right.
And we have an electromagnetic sphere just like a planet does. Well, not just like it.
Yeah.
But it has to do with our life force. Every time we move, every time our heart beats, we're going to send fluxes in that. It's not a stationary sphere that you're moving around in. So it's in constant flux, changes with your thoughts, with your moods, the temperature, the environment, atmosphere, temperature, everything. And it's constantly in flux.
Can I ask a question about that?
Yeah.
So what is your operational definition of life force? Because I think when people hear that, they might be like, "Ooh, life force, what is that?" So what do we mean by life force?
I do mean the force that resides within us all living things, really, that just keeps us going. So, for example, why does your heart continue to beat?
Because I'm alive.
Because you're alive. Why is that? Because there's a force keeping you alive, that energy.
Yeah.
That is life force. And then the vitality that you have as a human being goes away when that goes away. If I had a brain aneurysm, something happened to my heart and I just ended up dying, that life force would flee from me. It would no longer be measurable.
So all the energy going on in my body that's keeping me alive, that's my life force.
That's your life force. But that could also be augmented. So like if I have some TENS therapy treatments, so like we can put pads on you and like jolt you up.
Right.
That would be increasing your life force. If you put on the headset and the goggles and then went into a state of meditative coherence, that would be increasing your life force.
Right.
Eating the right foods increases it.
Which I need to do more of.
Now, what happens to your life force if you're going out, let's say somebody has a bender. They spend an entire weekend drinking, smoking, doing drugs, and just having a blast.
Yeah.
What does that do to your life force? You get a temporary boost, and then
it crashes.
Crash.
Yeah.
And so we have all those effects on us that affect our life force, short and long term, right?
Yeah.
So spatial relativity, taking those things into account, simply describes what we already know, that space fluxes around us. Why this is important is we now have a device that can measure that and that can see that. We can visually see the time dilation occurring. So when I say time dilation, what I'm referring to is a stationary. So like if we were stationary, we can see through the AIM device how time space is in flux. And with that device, we can measure it. But the idea would be, and I don't know that anybody's ever done this experiment, if we can create a clock sensitive enough with these devices, rather than cesium, we'd be using RNGs.
Right.
Then we would see fluctuations in time very similar to as if a body was in motion. Now, when I say in motion, I'm not talking huge amounts. So like, let's just say we were sitting here and you wanted to run to the store.
Yeah.
But you actually ran and you got in.
Rode my bike.
Or bike. And you just zipped down there, got the stuff, and zipped back.
Right.
Time dilation would have occurred.
Absolutely.
How much?
Very tiny.
Very tiny.
Yeah.
Right? Now, do you have a device that can measure that right now?
No.
No. But we know it happens.
We know it happens.
Right. So this is the same thing with the aim. We know it happens. We don't have a device at the moment that can definitively show that, but we have enough information about how the hardware works so that we can make that assumption. Based on the assumptions that we have, we know two things. Time dilates around it. Our consciousness affects it. Therefore, our consciousness affects fluctuations and causes time to dilate.
Right.
And I think this is part of a phenomenon that's even bigger than that, and that is our perception of how time passes. Because like we put people into meditative states, and I hear this all the time, that seemed like 5 minutes, but they were in there for 35.
Yeah.
Right? What does that mean?
Well, that is a lot of time dilation occurring within themselves.
Within themselves.
Yeah.
So what if those minuscule fluctuations of time can be perceived by our consciousness?
Right.
The scale change would be immense.
Yeah.
So what happened? Yeah. What if, when you're in a deep state of whatever, and you have a feeling that time is moving much slower? What if it really is? What if that feeling is based on our natural perceptions of time dilation? Yeah,
definitely could be.
And when you're out excited and having fun, and you're doing stuff, and you're like, oh my God, I can't believe the day's over.
Time flies.
It just flies by. What if you're actually speeding it up a little bit?
Yeah.
Affecting it in any way.
Right.
So we know that there are a lot of questions about relativity. Most people who are looking for a unification point of the laws of quantum mechanics and relativity are doing so from a speculative position that they could probably never test in their lifetime.
Black holes.
Black holes.
Yeah.
If you're doing anything on a black hole, it's probably not testable in the next 50 years.
Unless we can make them in a particle collider. But
which that would be not stable.
Even that, it would be for a fraction of a second. Yeah, it'd be difficult.
So we have to. So there's so much unknown. I think it's kind of dangerous, really, to completely dismiss things out of just disregard for newness.
Yeah.
Determining of the source.
Right.
You know, because a lot of people say, well, if I didn't read about it in Science Today, then what's the deal? If it worked, why don't we know about it already? Right. And that is most of science.
Yeah.
I mean, there's an immense amount of science that nobody knows about, but they're still using it.
It's a lot that I don't know about.
Right.
Yeah.
But we still use it. Yeah. I mean, like, you can't really say you don't really believe in it if you don't, unless you understand it.
Yeah. Because
like most technology, people don't understand.
Yeah.
So let me see. So this is an ethospheric modulator. And I think we covered everything that I had from the notes. Do you see anything that we may have missed with minus the math?
Well, let's just talk about that experiment for a minute. Of that, what we could do to really test. So you were saying before, spatial relativity. We have the math, we have the theory, and we can see it in action. What we haven't tested is with a clock, right? So that would be the next step. With I
mean, that would, I mean, part of my dream from the day one was turning AIM into an actual clock.
Right.
Yeah.
And so, right, what we'd probably want to do is get the highest precision we can possibly get.
No. Because that would be using a standard model of understanding it. I think we have to, well, no, let me back up. Yes, the highest precision, but not in the standard way. So I wouldn't say we needed an atomic clock to do this. We can create the clock. I think when we create a small clock. Now, let's say we got a quartz or something and we were to integrate it with that.
Mhm.
That's possible.
Yeah.
That's possible.
Mhm.
But when we're talking about literally measuring 10 positions of time together,
Right.
and then making them one, combining
Mhm.
them. So a regular clock is only measuring one line.
Right. It's one axis
It's
of
one.
time.
So
Yeah.
maybe 10 clocks.
10 clocks.
But yes,
yeah.
but yes, we do need verifiable experiments to show. I mean, this shows that it's happening. That it's happening, we don't need to prove.
Right.
But in order to really command and take control of it and to see exactly the scale, we need to develop
Right.
that. So when you donate or buy from us, that's where the money's going to go.
Yeah. Help fund this experiment. That's and another interesting thing that I thought about was time in dreams. And they did an experiment. I think this was Stephen LaBerge, famous lucid dream researcher. Really, well, there's several, but where they basically took some people who knew that they could lucid dream on demand, and they took them into a lab.
Wow.
And they asked them to, okay, when you're dreaming, give us a certain kind of eye motion that they could detect, and then count to 10 and then do it again. And so they actually measured the passage of time inside of lucid dreams.
Wow.
And from what I remember, most of them were actually fairly close to waking life, but there's variations to that. So sometimes, like, I've certainly had dreams very often in the morning, like after my alarm goes off, I go back to sleep for a few minutes. Those few minutes are sometimes when I have the most vivid
Definitely.
and long, really, dreams with the most content. And so it would be really interesting to put like a REM detector, which we actually have. I think it's in that box. Yeah, we have one of those. I haven't programmed it yet, but what do you call it? An eye mask. But basically it goes over your eyes and it uses infrared to detect when you're in a state of REM sleep.
Cool.
And REM is correlated to dreaming.
Yeah.
Not perfectly, but it's correlated with dreaming. And if you could plug a non-random event detector into that,
you could
and a clock.
Yeah.
Look at all of it.
Yeah.
And look for correlations between REM, between dreaming and dream recall, and what is, because presumably the better you can recall a dream, the more vivid it was. And so you could look at how it's affected not just in the waking world or in the meditation world, but in the dreaming world, which is where we spend a third of our lives. So why not why not try to make that better, right?
And understand it.
Yeah, exactly.
So much our brains are actually more active while we're dreaming than when we're awake.
That's true.
I've had those dreams where you wake up in the morning and this is what you fall asleep and you have this super vivid dream, and then at the end you're like, am I still asleep? Oh shit, I'm late. And then you wake up and you're like, it seems like you were just asleep for hours, but it was really just a few minutes.
Exactly. Yeah.
That is pretty wild. So time, we have an internal sense of time and we have an external sense of time. And the time is how we perceive events as they pass through us, by us, around us. And so spatial relativity, again, just gives us another level of understanding about time that might seem a little counterintuitive, but everything about relativity is counterintuitive until you really understand it, right?
Right.
I mean, like when
until you really do the math yourself and draw those space-time diagrams and how then it's really. But if you remember that the speed of light and is the same for every reference, then from there it does make sense that, or it follows logically that time has to slow down.
Right.
In depending on your frame of reference, if the speed of light is the same regardless of where you are.
Yeah, the speed of the light's not changing.
Yeah.
It's not changing. Not changing speed.
Right.
Not changing speed, and that is like this is how we know that light is changing because light doesn't just stop; it bends around things.
Yeah.
It follows the path of least resistance, no matter what direction it is.
Mm-hmm.
Right?
Yeah.
And so it's going around us all the time. So around our body and around our sphere is a state of continuous flux. The space is fluxing, so we know time is fluxing with it. We're not altering the speed of light.
Yeah. I just had another thought live on camera. Sunsets are basically, you talked about how light bends around things, but it does, obviously it bends around things. It also does, some of it gets absorbed, but some of it also gets scattered.
Sure.
And so sunsets are an example of Rayleigh scattering in the atmosphere. So I wonder if we could affect sunsets with our consciousness through the way that light scatters around.
Yes, and
droplets in the
actually I've
atmosphere.
seen this, but it's not that. Well, I shouldn't say that you're not. I think the biggest perception is how you perceive the color.
Yeah.
Because you can change your state of mind. Just like
That's true.
If you look at a candle long enough and meditate on it, it will appear to change color.
Yeah.
You can do those meditations.
Yeah.
Is the candle changing color?
Well, as it change, I mean, yeah, if a color is your perception of a wavelength, then yeah, it's changing color for you. But if is it changing the electromagnetic
Right.
frequency?
So if
right?
two people are looking at the same candle and there's a camera on it,
yeah,
those two people could see something different than each other, and the camera can see something different.
Yeah.
So because if the camera's looking at it, it's just going to look like a flame.
Yeah.
Because the camera is not going to change their perception.
Right.
But the people will. So having that same concept, if you're looking at the sunlight, you could change your perception of it. But how much of that would change the perception of what a camera's recording?
Right. Not very much.
Not very much, but I think it could. If we meditate, we're going to affect the space around us.
Yeah.
So let's say you had a whole bunch of people on the beach going into a state of coherence.
Yeah.
That could literally have an effect on the atmosphere. It's measurable.
Right.
I don't think it probably wouldn't be massive that the whole world could view, right? But for the immediate people that were looking at it could observe something.
Absolutely. And there's turbulence in the atmosphere and everything that can be local to that spot that maybe they're affecting. That's so.
Okay,
Yeah.
so I think we covered spatial relativity. For that, we're going to be presenting more of this at the Science of Consciousness, September 2020. And if you have any questions, you could leave it in the comments. We'll try to answer them.
All right. Like, comment, subscribe. That's what you're supposed to do. All right. See you next time.